All right, good day again. Welcome back. Today we're going to talk about chapter 4 again. This is chapter 4, section 4.6. Yesterday we talked about all those minimizing, maximizing functions. We were trying to find the biggest profit, the biggest area. Now we're going to finish off with figuring out the rest of really the class of functions that we have good behavior for in math, and that's polynomials. So today we're going to talk about polynomials. Tomorrow we finish off with rational functions, which are directly related to polynomials. And that's the end of chapter 4. So let's take a look today. Goals for learning is, as every day, what do we want you to learn today? There is a lot in this section, not as much as previous sections, but still a lot to learn today. Number one, we want to be able to determine if a function is a polynomial. In other words, if you're looking for one, what are the characteristics you look for a polynomial? Second, be able to find a rough sketch, and we're continuing to build that ability to sketch functions throughout the 153 sequence. But be able to sketch the graph of a polynomial from its base power function, be able to determine the x and y intercepts given a translation, and then be able to describe the function as it approaches an intercept. Or in other words, what function does it look like? What does that tell you as it approaches one of the intercepts that we have? So first off, probably definition, you're wondering, what is a polynomial? A polynomial is a function, or it's a sum of power functions, is one way I've heard it before, but it's a sequence of x raised to positive integer powers or non-negative integer powers with positive coefficients that are real. Specifically with this one, n greater than 0 and a of n not equal to 0. So in other words, what you're looking for with x is positive integer values. What you're looking for the coefficients are real values. And then possibly the best behavioral aspect of a polynomial is the degree of a polynomial. It's the highest power, the highest exponent, that has a coefficient not equal to 0. Now, there are a couple tricks that we're going to run into as you're copying down that definition. Probably wondering what some of these things are. Notice the last term, a of 0, is a constant. It doesn't have any x values attached to it. So let's take a look. Here are some values, or here are some potential functions. I want you to determine if each one of these is a polynomial, yes or no. So again, meeting our first learning goal for today, given a function, be able to tell if it's a polynomial. I'll give you just a second. There are 2, 4, 6 up there. Which ones are polynomials? Which ones are not? Let's go ahead and take a look at each one. Actually, let's poll the audience. How many of you think that 2 or more of them are polynomials? Okay, raise your hand. Yes, if you're watching on distance learning, raise your hand too. How many of you think 4 or more? 5 or more? Oh boy, okay. Let's take a look. First one, looking at each coefficient. Okay, first check, yep, all the coefficients are real. X to a positive power, yep, positive integer power, positive integer power, positive integer power. Coefficient, yep, okay, now f of x is a polynomial. Same reasoning, g of x is a polynomial. Now, why is it okay to have 2.5 in front of the x here? What if the 2.5 is in the exponent? Would that be okay? Nope, if 2.5 is in the exponent, nope, because that's a non-integer value. 2.5 being the coefficient, all it has to be is a real value. Yep, that works. H of x, simple one, 3x squared. Yep, that is a polynomial as well. Let's look at the last one though, or excuse me, I of x, 22.6. Is that in fact a polynomial? So there's no x in this one. How could I write an x in there? So in other words, if I wrote an x after that, and pardon my bad handwriting on that, what power would I raise x to keep the value still 22.6? Well, what if I raise it to the first power? Nope, then it's 22.6x. What if I raise it to the 0 power? Yep, that is okay. And excuse my bad handwriting, but 22.6 times x to the 0 power, that's another way to write 22.6 because x to the 0 power is 0. Our value is still 22.6, so yeah, that one's a polynomial. What about the next one? J of x, 7x to the negative 2/3. This one is not a polynomial for 2 different reasons. What are those 2 reasons? First off, it's a negative exponent. Second off, it's a fractional exponent. It's a non-integer exponent. So that one's not a polynomial. What about k of x? Well, let's ask the question, how could we rewrite the square root of x as x to some power? Let me find my pen here. There it is. What power would we write that to? And that's just a recall question. That's x to the 1/2. Let me put a little bigger one there. Yep. What's wrong with that? That's a fractional exponent, so that's, again, not a polynomial. It has to be a positive integer exponent. Questions on that? Now, there are a couple on those that are probably surprising. Probably I of x probably surprised you because that in fact is a polynomial. Then k of x is not a polynomial. Questions on that? Okay. Let's keep on going. The power function is kind of the building blocks. I had a professor in college that called it that way. It's the building blocks of polynomials. It's the building blocks of algebra. A power function is in the form y equals x to some positive whole number power. That's the entire function. An example like y equals x squared, y equals x to the 27th, y equals x to the 3rd. Those are the building blocks of polynomials. In fact, going back to our definition, a sum of power functions is a good way to define a polynomial because each one of those is power functions. So let's look back, some examples. The constant function y is equal to 1.8. What would the graph of that look like? Okay, that's just a horizontal line, y equals 1.8. Yep, no matter what you plug in for x, y is equal to 1.8. Linear function, y is equal to x. Just a review question, what's the power on x for that one? Yep, first, y equals x to the first power. And then quadratic, y equals x squared. If you take out your book for just a second, I don't do this real often, but if you could open up a book, and I'll put it under the doc cam here so you can see it. Turn to page 288. Now, it takes a lot of class time to copy these down, but before you go out tonight's homework, this might be a good idea. Let me zoom in a little bit on this. On the bottom part of page 288, there's the graph of the base power functions. The constant, the linear, the quadratic, the cubic. And then when we'll talk about tomorrow, that's a rational expression, or rational function, and then the square root function. Those are the base graphs, and that's what we're going to base our translations off of. So before you do tonight's homework, either look at that and maybe copy those down. Those will be key for what we're talking about tonight. Let's flip back to the computer real quick. And let's take a look. We're going to do a brief investigation here in class. We're going to take a look at some of these properties that polynomials have that we want to explore today. So we're going to look at, for each one of these, what's the degree? What's the number of turning points it has? And that's one that probably haven't talked about before, but a turning point is when a function goes from increasing to decreasing, or the reverse from decreasing to increasing. So it turns around. So kind of like the stock market, if you can imagine that. You know, if the stock market's going up and then it starts to sink, that's a turning point, or some event made that turn in value. Then I also want to look at what happens to x as it gets very large, and then anything else we notice, which is very broad, and I'll try to ask some questions that point to it, but anything else we notice. There's a lot of properties of polynomials that we're going to use through the rest of our book that we want to investigate here in this section. So let's first take a look at y equals 4 to the x, and here's what we're going to look for. We're going to look at its degree. We're going to look at the number of turning points it has, its behavior as x goes to infinity, and then any other aspects we notice. Now, even though you probably know this graph off the top of your head, let's go ahead and take our graphers out, our graphing calculators, and let's go and let's take a look at the graph and plot a new function, and our first one is 4x. Linear equation, slope of 4 goes through 0, 0 is both the x and y intercept. Let's go back to those questions and take a look. First off, what was the degree of this function? Yep, degree 1, x to the first power. And let me get my pen back here. Is our degree, x is to the first power. Let's flip back to the graph real quick. What's the number of times that it changes from increasing to decreasing or decreasing to increasing? 0. Never changes, it's increasing for all the values of x. So let's go back to, now again, degree was 1. Number of turning points we had was 0. And then let's look what happens as x goes to infinity. So as our x values get really, really, really large, what happens to our outputs? Those are going to infinity. So number of turning points is 0. And I'll just type this one in. As x goes to infinity, the function's values goes to infinity. So let's continue to look for a pattern. Let's look at our second equation. And our second one was y equals 3x squared. So let's take a look at that on the grapher. And delete this one out. 3x squared is our new function. Parabola, again, goes through 0, 0. Let's take a look. The degree of this, what's the largest exponent? It's 2. Go ahead and write that in. Our degree on this one is 2. Let's go back. Let's look at how many times it changes direction. So in fact, we have a nice break at 0. From negative infinity to 0, the function is decreasing. And from 0 to infinity, the function increases. So how many times does it change direction? It changes direction once. Let's go ahead and write that in. It changes direction one time. Then let's look again. As x goes really large, as it goes to infinity, the function again goes to infinity. And then let's look at our last one, which was y equals x cubed minus 2x squared plus 1. X cubed minus 2x squared plus 1. Either on your graphing calculator or here. Let's take a look. There's our function. This one, a couple more features to it. From negative infinity to actually at 1, negative infinity to actually at 1, this function's increasing. Then from 1 to, from 0 to about 1 1⅓, it's decreasing, and then from about 1 1/3 to infinity, that's increasing. So again, from negative infinity to 0, this function's increasing. From 0 to about 1 1/3, it's decreasing, and from 1 1/3 to infinity, it's increasing. So let's go back. Let's type in our pattern here. Oops. Our degree on this one was 3. How many times did this one change direction? Change 2. And again, as x goes to infinity, what does our function do? It goes towards infinity. Let's look for some patterns. Easiest one, of course, with all of these, what's the behavior as x goes to infinity? This one we can generalize for all power functions. And again, power functions have a coefficient of 1, but for all power functions, as x goes to infinity, our graph goes towards infinity. Let's look at the relationship between the degree and the number of turning points. And as we see with the degree 1, number of turning points is 0. With the degree 2, the function we looked at had a number of turning points of 1. At a degree 3, the number of turning points we looked at in that function had 2. So what's the relationship? What's 1 less? Yes. Now is that always true? No, that's our maximum. So as we take a look, any other aspects we notice? And let's go back to our graph real quick and look. There's our first one. Let's graph our second one. Here's our second one. Here's our third one. Let me put these in different. Let's put that one in a little deeper, a little wider line width. Okay, are there any of these graphs, are they ever broken? Do you ever have to stop and jump or stop and have a discontinuity? Nope. Do they ever have a cusp where they go to a point and then instantly change directions? Nope, they kind of flow smoothly. So some of the things we notice about all polynomials are generalized characteristics of them. First one, all polynomials have unbroken smooth curves. So some of your homework questions tonight, is this function a polynomial? If it's broken, in other words, if it has a jump discontinuity in it, if it has a cusp where it goes to a point and then bounces off immediately, that can't be a polynomial. They're connected, smooth curves. And then if your polynomial has a degree n, then it has at most n minus 1 turning points. Now, does it always? No. Sometimes, like if you look at the function just y equals x cubed, that's increasing for all values of x. That is 0 turning points. So at maximum, the number of turning points you have is 1 less than its degree.